Finding probabilities from a table is one of the hardest ways to find probabilities if you have to make the tables. But once you have the table, you can answer many questions about probability directly from the table, as long as you have the table. For example, suppose 100 people are interviewed and their age is recorded in the table below. We could find the probability a person is 40 or older, that's 17 out of 100. But remember, create problems. What if an intern spilled coffee and obliterated the last two columns? Now, we still know that n equals 100 people were interviewed. And the preserved values account for 83 people, so there must have been 17 people in the last category. And since the table gives the numbers of people of ages under 40, the remaining people must be 40 or older. And so we don't even need the entire table, we only need parts of it, and we can often deduce the rest of it. For example, suppose a computer error erases the sales figures for the first 3 days of the week. The remaining data is, and again, a problem exists whether or not we know how to solve it. Since we know the total, and the data shown gives us 31 sales, then we know the first 3 days must have had a total of 30 sales. So we could find the probability a sale occurred on the first 3 days of the week, 30/61. If we have a two-way table, we can also construct some missing data given some of the entries. So suppose we have data about the age of people and their financial status. Our table entries do correspond to mutually exclusive outcomes. And we have the row and column totals. And this means if there's only one missing entry in a row or column, we can find it. For example, since there are 25 people 20 or younger, and 24 of them are not millionaires, that means the remaining one must be a millionaire. And now we know all but one of the entries in the first row, so we can find the remaining entry. There are a total of 49 millionaires, and we've accounted for 38 of them, so we'll put the remaining 11 in the remaining cell. But wait, now we know all but one of the entries in the 50 or older column. So there's a total of 30 who are 50 or older, and 11 of them are in the millionaire cell, so there must be 19 that are not millionaires. There's also only one unknown in the 21 to 50 column. Since this column total is 56 and we've accounted for 37 people, the remaining 19 are in the remaining cell. And finally, we can compute the second row total and the overall total. For example, in a medical test for a disease, the test result is either positive or negative. The sensitivity is the percentage of those with the disease who test positive, and the specificity is the percentage of those without the disease who test negative. Suppose the test is 99% sensitive and 95% specific. If we test 10,000 patients, 10% of whom have the disease, we can tabulate our results as... So notice we have two pairs of complementary events. A person has the disease or does not. A person tests positive or negative. So we'll make one pair the row labels and the other the column labels. It doesn't matter which, although for reasons, it will be easier to use the presence or absence of the disease as our row labels. Note the specificity is based on whether or not a person has the disease, but we don't know that number yet. Now, since 10% of those tested have the disease, then we know 1,000 have the disease and the remaining 9,000 do not. Now that we know how many have the disease, we can use our sensitivity and specificity. Since the test is 99% sensitive, then 99% of those who have the disease, that's 990, will test positive, and the remaining 10 will not. Since the test is 95% specific, then 95% of those who don't have the disease, that's 8550, will test negative, and the remaining 450 will test positive. And, as always, we want to extend our row and column totals, and they should add up to the original 10,000.